Hello. As promised, I want to go over some mechanisms from lithium aluminum hydride reacting with a couple carbonyl compounds that we said were unusual mechanisms. So the ones I want to focus on today are carboxylic acid with lithium aluminum hydride and an amide with lithium aluminum hydride. The other mechanisms that we went over were reasonably straightforward: substitution, addition, those mechanisms. These ones are in that same class, but there's something unusual about them that has to do with the behavior of aluminum. And so let's look through these and see how they are very similar to what we've done, but with a key difference. All right? So again, when we're doing these mechanisms, anytime we see lithium aluminum hydride, I hope that you're thinking this is a source of H-. It is not an acid. It is a very strong base. It's not a source of H+. It's a source of H-. Right? So when you're thinking about these things, think about this as a source of H-. Right? This is hydride. It is H-. And it's important to know what the products of these reactions are before you get started. All right? So essentially have memorized that when you have a carboxylic acid with lithium aluminum hydride followed by acid, that you're going to produce a primary alcohol. Right? And those two H's come from lithium aluminum hydride. Right? The H on the alcohol comes from the acid quench at the end. Right? So when we think about what the mechanism is for this, let's get started. All right? And again, all the chemistry is going to happen from AlH4-. Right? And again, remember, this is a strong base. Always remember, when you have a carboxylic acid, that acidic proton is going to be the first thing to react. All right? All the nucleophiles we've talked about, lithium aluminum hydride, sodium borohydride, Grignard reagents, organolithiums, very strong bases. So the first thing is always going to be to grab that proton. Right? And so we're going to produce a carboxylate anion plus hydrogen gas. Right? And if you run this reaction, you'll see that bubbles start to form because you're forming hydrogen gas. So that has to be the first step in the mechanism. So we have to remove that acidic proton. And again, always remember that's going to happen faster than anything else in any of these reactions that we've been studying. Right? And then you get to ask yourself the question, all right, this is a carboxylate anion, not very reactive. Does it react with lithium aluminum hydride? All of the carbonyl derivatives react with lithium aluminum hydride. It's so reactive. Right? And so we have another equivalent of AlH4-. The hydride is going to add to the carbonyl. And again, we're forming a carbon-hydrogen bond. Right? And so that's going to yield a tetrahedral intermediate. And the byproduct is AlH3. Right? And the thing to know about AlH3 is it's still reactive. Right? There are only 6 electrons around aluminum. It's what's called a Lewis acid. Right? It does not have an octet. Right? And so what's going to happen is one of these O- is going to react with aluminum, right, to make a bond to aluminum, because aluminum now will have an octet. Right? So that we end up forming that molecule. Right? And that's the key. Right? If we were stuck here, we would get a completely different product. Right? And so it turns out that once we make this, right, this is now a leaving group. So the AlH3 serves like an R group in reactions of esters. Right? So once you get here, that looks a lot like an ester. So we can have the leaving group leave. And we generate an aldehyde. Once we generate an aldehyde, we can then do a lithium aluminum hydride addition again. So there's our second addition of hydride to form the second CH bond that we need. And then to get to the final product, all we have to do is add acid. And that generates our final product. And again, the acid only goes in after all of the chemistry is done, right? And that's a key thing to recognize. We can't stop this at an aldehyde because chemistry is still continuing with the lithium aluminum hydride reacting with that aldehyde, right? So the key in this one, deprotonation, form a carboxylate anion. Carboxylate anion reacts with lithium aluminum hydride to form the first CH bond. O- reacts with AlH3. That turns that oxygen into a good leaving group. Again, it's not going to leave as O2-, it leaves as O-. That generates an aldehyde. We do an addition reaction to the aldehyde. We get to a stable tetrahedral intermediate, and then we add a proton to generate our primary alcohol. When we look at the reaction of amides, amides are very curious because the carbonyl group completely disappears. So we end up with an amine. Right? It looks just like this carboxylic acid product in that we've added 2 CH bonds, but instead of ending up with an oxygen, we have nitrogen. Right? And so let's work through the mechanism to see why we end up with an amine instead of, like in this case, having an alcohol. Right? So lithium aluminum hydride will add a hydride to the amide. Right, we get to a tetrahedral intermediate. The important thing to recognize is just like we did up there, when you get an O-, that's going to react with AlH3. Right, so we're going to get to that tetrahedral intermediate. And now the interesting thing is you have essentially 2 leaving groups, right? You can have the oxygen reform the carbonyl. We can imagine that over here, and you lose N-, right? N- isn't a great leaving group, right? It's better than carbon minus, but it's not a great leaving group, right? So one thing we should note, this is really a poor leaving group, right? N-, not great. Here, when we have what can leave as O-, this is a good leaving group. Right? And this is the key to this reaction and why it does, why it gives you an amine and in the end, is because that O now is a good leaving group. So the lone pair on nitrogen can act to drive out the good leaving group. So this gives us our O- leaving group, plus now an interesting molecule that has a double bond to nitrogen. Right? And this thing is called an aminium ion. And an aminium ion is very reactive, and we can go directly to the final product by reacting it with lithium aluminum hydride. Right? That can add to that very electron poor carbon. You can draw a resonance structure of this where there's a full positive charge on that carbon, and that brings you directly to the amine. Right? So in this case, same ideas as we had up top with the carboxylic acid, but the key is that if you have a choice of N- as the leaving group or O- as the leaving group, O- is going to leave, and that gives you this aminium ion, which you can then add another hydride to and get to the final amine product. Right? And again, these are not mechanisms that I'm going to ask you to reproduce on a quiz, a problem set, an exam. But if they help you think about these reactions, because they are consistent with what we've been talking about, then please go ahead and use them. But again, we have a really nice explanation for what happens in these reactions, and hopefully that's useful as you continue to learn more about these reactions.